viruses and secure networks and things like that. And he's going to tell us quite a bit about that today, as well as showing us an example of the virus. So, Fred Cohen. You can leave.
This talk is about the 14,000th remake of Computer Viruses, Theory and Experiments. I'm Fred Cohen. And I'm not so new, well, all right. Start with the definition. A computer virus is a program that can infect other programs by modifying them to include a possibly evolved version of itself. With this infection property, a virus can spread from program to program, from user to user, from computer to computer, and from network to network, infecting everything in its path. The way it works is every user that runs a program that's infected runs the risk of infecting their programs. When somebody else runs those programs, they get infected. When somebody else runs those programs, they get infected. A simple virus, well, let's show you a simple virus. I have this policy. The policy is I will not show anybody a real virus no matter what, ever. So what I do is I use pseudocode. So this is a pseudocode virus. It starts out with a header up here, 1, 2, 3, 4, 5, 6, 7. The purposes will become clear in a moment. The main program consists of the run the routine infect executable, then if the trigger is pulled, do damage, and go to next. Okay, so the infection consists of, go find a random executable file. If the first line is 1, 2, 3, 4, 5, 6, 7, then we'll assume that it's already been infected, so we'll look for another one. If it hasn't been infected, then we'll prepend this, the virus, to that other file. Okay, so this is a virus that prepends itself to other programs. Oh, the trigger pulled can be any condition you want. The do damage can be any condition you want. Finally, unless it never leaves this routine, it'll go to next, which means it'll run the program that it was prepended to as if nothing had happened. Give you an example of what a virus in operation might look like. This is, let's see, the NSA told me I'm not supposed to reveal the names of any systems that a computer virus can work against until such time, until such time as the defense is designed.
That's right.
So that means I can never use the name of any computer system ever. So this is a demonstration using the command language of one of the most popular operating systems available today, written primarily in the C language. I know you won't be able to tell from the commands what operating system it is. Do a listing of the current directory. You might see program A, program B, and program B. Program A prints out its name, and the one I'll show you works just like this. Program B prints out its name. Program B, surprise, says it's infected, goes and infects another program, and then says this is program B. When we then run program A, it will say, well, I'm infected, and it'll go and find something else to infect, maybe program B, and then program B will be doing the same thing. It'll, in this case, say nothing left to infect. Of course, instead of saying nothing left to infect, you could, delete all the files, or maybe make your spreadsheet come out with the wrong answers once every 17 times you run it, or whatever you want it to do. Here's sort of a picture of the process. We start out with P1 infected, P2 not infected. User U2 runs program P1. The virus prepends itself to P2. Then P2 executes. Then P1 executes normally. Somebody subsequently runs P2. They get infected, and so on. All right. Now, I was told that you're not all computer experts, so I'm going to put it in terms that worked on my secretary. We were getting so many phone calls, she came in and said, "What's a virus?" And I said, "I only have 2 minutes. Let me see, what can I do?" And I got out some memo pads, and I said, let's imagine that we have a bunch of secretaries that know how to do different stuff. Say one of them knows how to write a memo, write a letter, take dictation, etc. A different one knows how to do the books, make a call, make copies. Now, I'm going to write a memo on top of this memo pad that says, write a memo on the top of it. And it's going to say, in your own words, copy this sentence onto all the other sheets. And if it's after 1990, burn everything in sight. some other secretary borrowed your information on how to write a memo, that all of the things that that secretary does would then have copies of that message, if it's a faithful secretary who does exactly what she's told, like most computers. Then if Secretary 3 said make a call, which had then been infected, Secretary 3 would get it on all those memo pads, and Secretary 4 might do something from Secretary 3, and so it spreads. The logical conclusion is that after 1990, we're going to have to start a new office building. Then there's the newspaper analogy. This one I sort of like. Let's imagine that we have somebody that can talk to some important newspaperman that says, Gaddafi ordered, let's make something really wild. Bombing of a discotheque. There you go. Well, you might have a whole bunch of these reporters that go and tell other reporters, and they tell other reporters, and they tell other reporters, and before long, everybody in the whole world, or at least everybody in the United States, believes that this thing actually happened. Now, despite all efforts to undo that particular mental version of a virus, there are still people in the United States that, if asked, probably people in this room, that if asked, will tell you Gaddafi ordered the bombing of this discotheque in Germany. So now we see part of the problem of eliminating viruses. That is that once you're corrupt, it's very difficult to purify you again. And they also ask AIDS patients about that. Some misconceptions. There's this program at Xerox several years back called the Worm. Now the Worm, it turns out, is not a virus, but it was sort of interesting. What the Worm did was it looked for computer systems in the Xerox internal net that were not being used. They were shut off for the evening, and it would use those systems to perform computations and have this big parallel computation using all the unused resources in Xerox. What happened was a bit flipped, and one morning people came in, and when they rebooted their computers, instead of giving them back the original operating system, it gave them back the Worm. Now, Xerox had to shut down their entire internal computer network and start it all up from scratch with a clean disk from whatever to get this everything booted up correctly. Now, this is pretty bad, but it's not as bad as a virus. The reason is when they turned everything off and turned it back on, it was all back to normal. If this was a virus, it would have infected those systems, and when they turned it back on, they would have found that it still worked that way. And in fact, when they went to backup tapes, if it waited a long time before displaying this behavior, the backup tapes would contain that infection. They might have to lose a substantial amount of work. Another thing is core wars. This was touted in Scientific American a couple of years back. It's two programmers doing battle with their programs. Programs try to halt each other. Real exciting. Well, if you're here at night, real late, 3 in the morning, and you're a hacker, and that's what you like to do, then good for you. And there was the use of the term virus in the APL, which sort of is a misnomer because there was no infection process. This virus was simply something prepended to any APL routine that said, rather than interpreting this with the standard APL interpreter, send it through this macro interpreter. So that there was pre-interpretation, so you could make more general operators. So the differences between viruses and other attacks are concentrated in this word infection. This is the thing that makes a virus, and there are some ramifications of that. One major ramification is persistence. That is, a virus remains in the programs or data that it has modified. It remains there indefinitely. That means that backups provide safe harbor. By example, if I have an infected disk and it waits till 1990 to do damage, and I'm doing backups from now till 1990, when 1990 comes along and it deletes everything in sight, I go back to 1989, and that disk also says if it's after 1990, blow everything up. So those backups are safe harbor for that virus, and it sits there, and in effect, the ones at Lehigh University and places like this, they haven't cured it at all. Somewhere, somebody has a backup disk, and a year from now, or 2 years from now, or 10 years from now, they'll bring that disk out and put some program in, and it'll all be up again. Another feature of viruses is their generality. That is, they can carry along with them any information that you desire to send. That means they can carry any program. So they don't just have to delete everything in sight. They can subtly modify data files. And I'll talk about some classic examples of that later on. Like classic, Anything more than 2 days old is classic. The other feature that's really severe is the extent or the range of the virus. Because it spreads transitively, that is, if I give it to you, if I can talk to you and you can talk to you, then I can talk to you through you, okay? So it spreads from user to user to user. It reaches the transitive closure of information flow, which means I can write a virus at my PC in the University of Cincinnati, and it can be designed to spread through other PCs, into mainframes, through mainframes, across networks, and eventually get to everywhere. Let's see.
Well, that statement sounds a little bit too general. If we're just transmitting data back and forth and not programs,
What's the difference?
what's the difference? You don't execute data.
Ha. Not even close to true. Let me give you an example so I can move on. I'll give you an example so I can move on. Profs. You've heard of profs.
Okay, yeah, I understand that.
Profs has a thing called data. You know, you might mail somebody a document in profs, and it might have an SY command in it that says, attach this line to every other profs file that you say.
I'm familiar with that problem. I consider that to be a program.
Okay, well I'll address that issue momentarily. I didn't say it was hopeless yet. In fact, there's a great deal of hope, but it may not be very pleasant. Before I do that, I want to show you, well, I claim that there's at least one good virus. And I'm going to show it to you right now, at least how it works. It's a compression virus. What it does is it spreads from program to program, compressing everything along its way. And when you execute the programs, it decompresses them before execution and therefore implements a particular time-space trade-off, which could be considered virtuous if space is expensive and time is cheap. Here's how this one works. We have an infected program. Let's see, one of the interesting things here is this one's not a Trojan horse. It asks permission before it does infection, right? Therefore, it does not do something that was not advertised. It only does what it advertised. So, can I infect this file? You say certainly. Then it's your own fault. First thing it does, it'll find another file, say P2, and it'll compress it into P2 prime. Then it will prepend the virus, the P2, then decompress P1 prime back into the original uncompressed version, P1, and execute P1 normally. Okay? So this is a virus because it infects other programs, and it has some potential benefits. So much for the good viruses. People have suggested that you use viruses to defend against viruses, and I've suggested that if somebody modified one of your defense viruses, you'd be in big trouble. Here's a denial of service virus. Oh, the subroutine trigger pulled, this was done in 1983. So the subroutine trigger pulled is if it's greater than 1984, then return true, and do damage is an infinite loop. So you can imagine that January 1st, 1984, every program would be an infinite loop. There are some properties that allow viruses to exist. In particular, information can in general spread to the transitive closure of information flow from the initial source. Information paths are present whenever users share information. There's no fundamental difference between data and program. And by example, well, profs of course is an example, the language BASIC. Typically you can edit a BASIC program with a text editor, just as you would edit any other text. But when you use BASIC, it interprets that text. And in general, information only has meaning in that it's interpreted. Okay? So what that means is that any information can be interpreted. If it isn't interpreted, it has no use. In its interpretation, it may cause infection, depending on the means of interpretation and the information being interpreted.
Well, that's too general. I mean, the only interpreter that applies to information in human beings, you can't get the virus through the usual channel.
Really?
I agree with the basic thing you're saying, but I think it's too general.
Well, it is a general principle. It's true generally. That doesn't mean that in every specific case it is necessarily going to happen. Okay? That is, human beings can certainly perform infections. I mean, if you wanted to be a heretic about it, you could claim that the concept of God is a mental virus. Okay. And then if you wanted to tell me that human beings don't spread these things, I would be hard-pressed to agree with you.
The difficulty with the data program issue is that the virus has to be constructed differently for each different interpreter. And
Oh, not necessarily.
as you talk about having lots of different interpreters for the virus, you've got to cope with the fact that it's going to be dealt with that way.
Yes, but in fact, you can write a basic program that infects basic programs, Fortran programs, assembly programs, executable code on 400 different kinds of computers, COBOL programs. So, and it's larger and larger. Yeah, that's right. It's more difficult to write more general types of viruses than less general.
Undetectability, because most of the ones so far.
I'll get to it.
Unlike the earliest.
How about this? I promise that I will answer all questions, probably before the end of my slides. But if I haven't answered them by then you can chime in. All right, any policy. Now, we've proven mathematically that any policy that allows transitivity, sharing, and general purpose interpretation cannot prevent a virus from spreading to the transitive closure of information flow. What that means is, I know, you're jumping. Okay.
You've proven that?
Yes, mathematically. You can read the mathematical proof if you have the guts to look at this.
I don't like generally.
Good. Steve has a copy.
Good.
Steve has a copy in all of its gory glory. And I'm sure you're welcome. What this means is that any policy which prevents a viral attack has to limit these properties in some way. Which means prevention depends on limited sharing, limited transitivity, or limited interpretation. Now, limiting transitivity is a very interesting idea. And I've looked into that, but been unable to do any real experiments because it's very difficult to get a hold of a system that has limited transitivity. None exist, and I don't have enough money to build one. Limited sharing, well, the problem with limiting sharing is that we all like to talk to each other a lot. If we have no sharing, we have no communications, and then we lose about more than 50% of the utility of computers. Of course, without sharing, that means we can't use a program that somebody else wrote, which means we all have to start by toggling the switches on the front of our old computer and toggle in a loader, and then maybe toggle in a program that lets us type on the keyboard and work our way up from there. And that's not a particularly pleasant type of thing. The other possibility is limited interpretation. And this begins to address the sorts of things that you're talking about. If I have very limited interpretation that is not Turing capability, then it's conceivable that I could have programs that do all sorts of things that would not allow infection. By way of example, I can have a simple database program that allows me to look up something in the database and retrieve it, and maybe enter something into the database and store that in the database. And it may be that I cannot write a virus with that limited functionality. Now, there are a very large number of applications in the world that are that way. It's possible, presumably, to write a spreadsheet system that works this way, a document formatting system that works this way. It may even be possible to have these things communicate with each other and have it continue to work this way without general purpose interpretation. But don't put NOR into your database, because NOR is a sufficiently general operation that I can implement anything with a sufficiently complex sequence of NORs combining information together. So it's fairly limited. I also needed a way to address things, by the way.
Right.
Yes, sir.
Multi-screen system, is that?
Well, I'll get to that. Hard to believe. I'm going to get to it right now. Talk about limited sharing. Let's see. The so-called security policy, quote unquote, implemented by, theorized by Bell and LaPadula and implemented subsequently, I'm certain, is the standard military model of security. That is secrecy. The way it operates, if I'm at a given level, I can not write information of a lower classification, lest I could declassify information. I cannot read information of a higher classification, lest I could read secret information, even though I'm not cleared. That's the Bell-LaPadula model. Now that prevents us from leaking secrets, well, except through covert channels, which we may get to later if somebody asks. The problem is, the least trusted user in such a system can write a program that can be run by any other user on the system. So from the standpoint of viral attack, the least trusted user is the most dangerous. And this, of course, is exactly the opposite of what we associate with security. But this is not a security system, it's a secrecy system. If it's properly designed and implemented, it can indeed prevent leaking secrets. But it can't prevent corruption of integrity. Well, there is an integrity model. It's called the BIBA integrity model. And it's just like Bell Padula. In fact, it's a mathematical dual. And what it does here is if I'm at a given integrity level, I can't read information that's lower integrity, lest it would corrupt me. And I can't write information of higher integrity, lest I would corrupt it. What we can do, of course, is combine secrecy and integrity together, and what we get is a system like this. Information. You can't read or write information that's higher or lower level than you. And this, of course, is limited sharing. There are many cases of this. I mean, you can, if these levels are broader than those levels, things work out differently, but it leads to systems that have the same properties, isolation. Without going through all the steps along the way, we can generalize this. When we generalize it, we get a poset, a partially ordered set. A poset is a transitive, reflexive, anti-symmetric relation. That means these properties hold true. Isn't that nice to know? Imagine that information flows up. Okay? If I have information here, it can corrupt information here, 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 and here. It cannot corrupt information here because there's no path by which information can flow from here to here.
Could you point to the...
Do it on the chart so we can see.
Yeah, sure. That's why I'm here. That's why you're paying me so much to be here. If I have information here, it can spread, information flows up only. Information can flow up to here, to here, to here, to here, to here. It can go to here, it can go through here, but it can't get to here no matter what, because there's no transitive path that takes it there. So that's the limit to the corruption that can be caused by this. Similarly, we can analyze the limit on the amount of secrets, say, that can be leaked from this place in the graph. Nothing can be leaked from here or here or here or here or here, but we can leak anything from here, here, or here. Okay? Because those are sources of information. And in fact, if you put this into the right form, into a matrix form, then you find that you can determine the effects of collusions of individuals by oring the transitive closure or flow into or out of them. And that consists of oring the rows in a matrix. So it's very computationally feasible to analyze posets and systems like this to find out not only the maximum effects of an individual, but the maximum effects of collusions of individuals, and also potentially to trace down what individual could have caused a set of circumstances to occur.
These systems have no conversation, no two-way communication, right?
That's right, it's one way. Well, it's not explicitly true. You can communicate between two individuals in the same place in the graph. That is, if I can talk to you and you can talk to me, then we are equivalent. From the standpoint of information flow, we're equivalent. Right? So that's really what it means that we can talk to each other. I mean, maybe your boss never wants to hear from you, and so they can put you up at a different place.
The other way around.
You might find that you never hear from him when pay comes around either.
Affect us too?
It will affect you, I don't know. Well, another possibility is limited transitivity, and here I have the worst possible pictures. So, bear with me. The basic principle of limited transitivity, well, here's an example, is the distance metric. And the way this works is every process has a distance associated with its output, which is the maximum of the distance of any of its inputs. Okay?
Go to the screen.
Yeah, unfortunately, you blocked a third of the room when you talked up close to the machine, so
Right.
if you went to the screen, that might help.
I'll repeat it on the other side. What I need is a bigger pointer. Essentially, we maintain a distance matrix, metric for every process and every file, let us say. The distance of the output of any given process at any given time. All right. See? Classy organization. Everything you need to do. The distance of the output of a process is the maximum of the distances of the input. The distance of a shared input is one more than the distance of that same input if it was not shared. And information is accessible if and only if the distance is less than some constant. Okay? you can imagine that I could talk to my boss. Suppose we limited the flow of information, right? I can talk to my boss can talk to his boss. If we have limited transitivity with distance of 1, I can't go over my boss's head, right? I can send something to my boss, but he can't send it on because the distance would be exceeded, and if the operating system implements this policy in the correct fashion, then I can limit the transitivity of information flow without entirely restricting information flow. And this little picture down here is this bizarre way of thinking about it, where you say, if I'm the blue person, I can send information to here, or get information from here. If I'm the green person, I can go through this loop. So blue can talk to green, and green can talk to blue, but there's no transitivity. Blue cannot send to green to red. If blue creates something, or is involved in it, it can never get into red, okay? It can only get into this blue circle.
The example you gave in the beginning is where I infect all of your files.
Yeah.
Now,
That means that each of those files would contain information that had flown a distance of at least 1, right?
so you have to so it's not just,
That's right.
Not just
I'll get to
information I
that
send
problem
you.
in a minute. I know what you're thinking. I'll get
This
there.
is something that doesn't exist, right? In prep, that you mentioned. That you couldn't
There is no system that does this right now. I've, made meager attempts at implementing simulated versions of it, and it works fine, except, well, there are some problems. I'll get to the problems. After I get through all these systems, then I'll tell you the big problem with limiting information flow. Some of you probably already know it, but for the rest it may be a surprise. I just want to note that the space for such a system is that of keeping a D for every object in a system, and the system overhead is constant, and you do 1 check per access. Okay, so it's a very efficient mechanism. We can implement this in all practicality. Well, except for the thing that I'll tell you about later. Now, we're now completely out of the original slides. The original slides were all done on a computer that was able to print out characters, and now we're moving into the I drew it in my spare time mode of operation. So this is, we didn't know this in 1983. That's what. This is the flow list model. Now, the way this works is it maintains a list of all subjects which have affected each object, and it limits the access by allowing us to specify a metric on the list. In particular, the flow list of the output is the union of the flow list of all the inputs. Information is accessible if and only if some Boolean function on that list is true. All right, so now we have, for each subject, some subspace of all possible sets of subjects, some subset of those subjects. And if only people in that subset have affected it, then the Boolean function is 1. And the space required is the number of objects times the number of subjects, plus the absolute value of the size of maintaining this Boolean function, which could grow as large as this, times the number of subjects. Then the time is equal to the time to do this evaluation. It depends on what evaluation we want to do. Typically, this is also reasonably efficient, and it's a little bit more general than the last one. We can go real general and get to the flow sequence model. And this is sort of as general as you can get. This says, instead of maintaining just a list, maintain the sequence of subjects affecting an object, and if that sequence is legitimate, you can use it. So I can only use something if Joe wrote it and Bill approved it. Well, then I can look at it. But if either one but not both, or if the latter did it first and the former did it second, I couldn't look at it. The problem here is that all possible sequences can be, well, it's infinite, and therefore whatever Boolean we use to determine whether information is accessible is also potentially infinite. So the amount of space and the amount of time required is infinite. For those of you that are concerned about generality, there's a problem. The problem is called the precision problem. Here's what happens. If we want to precisely maintain all of the information flows, every source of every bit of information that has affected every bit of information in everything everywhere, then we have a problem, and we're usually going to use conservative estimates to resolve the issue. Okay? What happens here is, if we use conservative estimates, information can be unjustly deemed unusable, and that results in denial of access, which is bad. Either isolationism results, or we have to have some stability point in our system. That is, things become inaccessible if we don't properly deem them accessible or not. So either we reach a system that has all isolated stuff, as nobody can talk to anyone, or we reach a system in which there's some stability point. Okay? Here's the problem. A stability point implies that there is a quote-unquote, I guess it's quote, precise, end quote, system for that point. Denning proved in about 1982 or 81 or something that precision in such a system is NP complete. What that means is that either we have a system that moves towards isolationism or we have a solution to an NP complete problem. What that means is that if we actually try to implement one of these things, we're either going to have a system that tends towards isolationism or it's going to take forever to determine what to do. Here's a pictorial version.
Sounds like the government.
Well, there you go. We can use it for military systems. Just think, we could end war tomorrow, right? It takes forever to decide to do something we never want anyway. Well, precise is NP complete. If it's not NP complete, it means it's not stable. That's this little brown circle with the arrows going in. So we have this system that, as t goes to infinity, is collapsing towards this only stability point, that of isolationism. The point where all the information that can ever get anywhere has gotten there, and nothing can ever get any further. So nobody can share anything, and it all gets bound up. And this has been observed, actually. In Bell-LaPadula-based systems, there's a tendency for information to move towards the highest classification level, and since nothing can ever go down classification levels, everything becomes highly classified. No one can ever look at it. In fact, I've been at conferences where I was not allowed to listen to what I said. If we push it a little bit further and go to more general systems, we have a paradox. And what happens in this case is, suppose we have a rule that says C is allowed to access a bit from A or B, but not from A and B. As if one or the other has changed it, then we can access it, but not if both have anything to do with it. Well, let's suppose we're going to perform an OR operation on 2 bits, 1 bit from A and 1 bit from B. Well, if A is a 1, A or B is equal to a 1 regardless of B, and therefore we can look at the result. Right? If B is a 1, little b, the bit from big B, little b is the bit, big B is the subject, then A or B is equal to 1 regardless of what little a is. So we can look at it. And in fact, if they're both 1, then A or B is 1, and we can look at it because we don't know which one or both. We don't know if it was one or the other or both, so we can still look at it. That should be accessible. Here's the problem. What if they're both 0? This is the only case where we're not allowed to look at it. A or B implies A and B. It tells us information from both, and therefore we have to deny access. But if we deny access, then he says, wait a minute, then I know they're both 0. So I can't deny access, or they know what it is, but I can't give them access or they know what it is.
Just lie.
Give them a random number, right? This is a paradox. What it means is that precision now, in the general case, is worse than NP complete. It's just flat impossible. Here's a summary of what I just said. I thought you'd be interested that I put it up, but I just said it, so why should I bother saying it again? You're all quick enough, you can pick it right up. Most of the people I talk to don't understand anything I said, and I put up the chart and they still don't understand. There is the issue of detection in Pure. There are a bunch of questions that we might like to ask and things we might like to find out about, and that's why I'm here, so I'm going to answer them and tell you about them. Is X a virus? Given that X is a virus, can we find all the infections caused by X? Is there a statistical method of detection? If we find a virus, can we remove it? And then can we do that without denial of services? That is, can we do it while the system's running? There's a story of the Thompson C compiler you probably all heard about. There's complexity-based integrity maintenance, which is also known as software self-defense. Software self-defense. We have N-version programming, vaccines, user awareness, instrumentation, all this stuff, and so I'm going to tell you about it all right now. I don't want to give away what's going to happen.
Can you tell us about the Thompson C compiler? Not all of us are...
I'll tell you all about all of it. At least more than you probably want to hear. Less? Okay, well, I'm available later, and I have probably 400 pages worth of papers here that you can go home and read for the next 3 years, and hopefully you'll understand it better than my committee did. Question 1. Is the program CV a virus? My committee had a lot of smart people. Is CV a virus? Well, I don't think so. I know I can't tell. Suppose I write a program called D. D is a decision procedure. It will look at a program and determine whether or not that program is a virus. It will tell me in finite time it's a virus or it's not a virus. That's one that you wrote. I didn't write it. You wrote it. You claim that it's such a program. And now I'm going to prove that you're wrong with one general purpose version. Here it is, the main program of my previous version of a virus. If your decision procedure says that this is not a virus, then infect an executable and do that other stuff. If your detection program says it is a virus, oh, then don't do any of that stuff. So if you claim that I'm a virus, then I don't do infection and therefore I'm not a virus. But if you claim I'm not a virus, then I will do infection and therefore I am a virus. So whatever you say, you're wrong. And this is a general problem here. It's called undecidability, and the formal proof does not depend on this stuff if you really want to know.
Isn't it, and I agree with that, I'm not arguing with that at all, but isn't it possible to give a D that sometimes gives false positives, but is still...
Yes, in fact, it's possible to have a D that sometimes gives false positives and sometimes gives false negatives.
Well, no, in just false positives.
No, I think not. Well, yeah, certainly. Absolutely. It says everything's a virus. And now we have to verify every program everywhere.
But in general, talking in terms of usefulness as opposed to theory, this doesn't really impact on having a virus.
It really does. You see, because any compiler is virus. And that's a problem. So then we're going to start detecting all sorts of things like compilers and interpreters and,
Okay, but
you know.
that's a practical observation. It doesn't really depend on this.
No, but all I'm saying is that we can't do a perfect job of it. I didn't say we can't do anything. I said we can't be perfect. I think most of the bosses here knew that you couldn't be perfect, even if you didn't believe it yourself. Very few people believe they're perfect, but those that do are typically programmers. This is a lousy example, so I'll ask you to mostly ignore the example, but I'll get to the point. Can we find all the infections from some virus? Given that we have one copy of a virus, can we determine whether or not some other program has an infection in it that was created by that virus? And the problem is that there are these things called evolutionary viruses. And I didn't bring the slide that proves that it's undecidable. It's the same thing as before. That is, if your program says that this program is infected, then that program won't do an infection. And if your program says that that program is not infected, then it will do an infection. And like that. But the basic principle here is that we can design viruses that evolve, and they can evolve in very tricky fashions. So I'm not even going to bother going through the details here because it's not.
That contradiction you just gave didn't involve it. Right?
Didn't involve what?
Evolution. The thing which said if your program says it's infected, then don't.
No, that's the
nothing
first version.
evolutionary in there.
To be slightly more formal, that's the Aleph not proof. The Aleph 1 proof is this one. The key here is that suppose we find one instance of a virus, and we say, here it is, I'll look for every other copy of this virus. Okay? I can write a program that evolves, so when you look for a copy, there won't be an exact copy anywhere.
But the all if not proof showed you could do it without writing an evolutionary virus.
No, but I'm going to say, wait a minute, I have a brilliant programmer who's better than any computer anywhere ever, and he can look at this one instance and say, here's a virus. Now, does that give me anything? Okay? And the answer is, yes, it gives me, I caught this one virus, but it doesn't mean that I can catch all of its progeny. Okay? Maybe if that was already obvious to you, it's a deal.
If I tell you here's a virus which will not allow you to catch its progeny, can you tell me, therefore, that's an evolutionary virus?
Yes, absolutely.
But your Aleph not proof didn't involve evolution at all. That was a constant virus.
No, but you told me it's a virus. Yeah, all of its progeny are identical if it doesn't evolve. The definition of evolution means that it changes, therefore I look for identical sequence.
Vincent, the first one says I can't detect a virus just by looking at it. This one says, even if I already have found one, I can't detect its children. In other words, in this case, you've already got more information than you did in the first
No,
case.
he said that there was an argument of the same form for this case.
Yeah.
It is, it's of the same form, but it's not identical. Look, I'll tell you what. I'll tell you what. We'll save everybody a lot of time. I'll show you the formal proof. Stop by later. The point is that given that we know that a given sequence is a virus, constitutes a virus, that does not allow us to find all of its progeny. So next time I'll bring the right slide. Good enough? All of this leads to the issue of, can we remove a virus? And I'm just going to point out the problem of removing a virus if we don't have denial of services along the way. Suppose we have these two infected programs, and we cure P1, but in the meanwhile, P2 goes off and infects P3. Then we say, oh, I found P2 is sick. We cured that, but in the meanwhile, P3 infected P1. You may note that the issue of whether we have more viruses or more cured programs around depends on the amount of time it takes to figure out that a virus is somewhere and cure it, as opposed to the amount of time it takes to infect something else, given that we already have these infections around.
Unless you lock down the system while you're...
That's right, unless you deny services.
Okay, yeah.
Yeah, that's right, that's what I said. That means that if we're going to cure a virus, unless the virus is very slow, then we have to deny services.
Wait a minute. Inspection.
That's right.
You're making statements that are much too general. I don't think that's the case. If you can figure out a means of preventing further infections, say that any program which tries to write an executable program will be stopped.
That's denial of services, because normally the services that are permitted include being able to write executable files.
Yeah, you couldn't run your compiler if you can do that.
Right? So you can't run your compiler, so you're denying some services. I didn't say you have to turn everything off.
All right. Okay. I thought that.
I said you have to deny some services. Which ones? That's an interesting question. There's all sorts of research to be done. You know, I don't want you to think that it's all solved. I want you to understand that none of it's solved, that we need a lot of work to solve it all. This is the my version of what the Thompson C compiler is and what to do about it. Well, one thing we might try to do, might win or might not. The Thompson C compiler consists of a source for login, which is clean, and a source for the C compiler, which is clean. This is under one of those operating systems I can't talk about. And then an executable, which is infected. Well, it may not be infected. It contains a Trojan horse that says, let Thompson log in. And the C compiler contains a Trojan horse that says, if you're compiling the login program, then add let Thompson in. And if you're compiling the C compiler, then propagate this bug. That's where it becomes viral. All right, so here's what happens. If we compile a clean login exec, we get a clean login source, we get a dirty login exec. If we compile a clean C compiler, we get a dirty C compiler. What do? Aha. We'll write a real funny looking C compiler and compile it with the sick C compiler. Then we might get a clean version of a lousily written C compiler. Right? Note that the more poorly written the C compiler is, the funny looking one is, the less likely it is to be recognized by CC exec. So the solution is get a freshman. Right? In other words, for high integrity, we need lousy programmers. Right? You've solved that problem. Here's another one. This is for detection only. This is a complexity-based integrity maintenance mechanism. I mean, notice the names are getting longer. This is how you can tell that things are getting harder and harder, because the names of the papers keep getting longer and longer. The effect of, the effect of gamma rays on the man on the moon miracle. This is for, primarily for untrusted computing bases, things like IBM PCs.
Not allowed to mention it.
Excuse me?
Not allowed to mention it.
No, this is a defense.
Oh.
I can talk about defenses and anything, I just can't talk about attack.
What's the point of defense on it? You can't be attacked.
Must be implying
can't talk about
I can't tell you whether or not it can be attacked, I can just tell you whether it can be defended. But I am allowed to tell you that no system currently available absolutely prevents viral attack. So you can then derive whether any particular machine. Now, from IBM, you believe that the PC is no longer available, and therefore maybe it's safe. have programs that depend on other programs and data files that depend on programs and things like that. What we can do is write programs that check themselves, check their data files, and check other dependent programs. Okay? Now, to be any good, by the way, these little notations here talk about the fact that we have a subroutine version of this thing that works. We have a check disk that does these things. These are just, when I talk to people that are into real world stuff, not theoretical people like you, I tell them all these things. We have your guy has a copy of the program, so don't worry about it. Check function has to be, well, here's the problem. If our check function is one of these regular old get a checksum type programs, then it's going to be awfully easy to get around it if I'm any kind of a serious attacker. So what has to happen is the check function has to be very hard to identify. One way to do that is to have an evolutionary check function. It has to be hard to locate, which means maybe we'd like to randomly insert it into different places in different programs. Then it has to be hard to forge, which is to say it has to be difficult for somebody to either modify the program and have it produce the same checksum, or modify the checksum and have another program produce a proper checksum. And we've done this. We figured out how to get around this for the most part. Evolution, essentially we pre-process things into source code before compilation. And we can evolve the source code in the same way as a virus can evolve, and this may lead you to understand what we mean by survival of the fittest. Insertion, well, maybe the user selects locations, or we use random insertions. Hard to forge. Well, it turns out, this is the strong part of it, we used an RSA-based pseudo-random number generator that has a user-selected key, and the problem with the RSA historically has been that it's very slow. And what we did was we found a way to do a checksum of a file, a cryptographic checksum of a file that's approximately as strong as the RSA, while performing at a sufficient rate so that you can checksum a 1 megabyte file on a standard IBM PC with a hard disk in a couple of seconds. So it's quick enough so that you can include it in programs. And it essentially takes blocks of things through a trapdoor function into successive rounds of an RSA to do its thing. So what this is a self-defense technique that you can put into programs. They can maintain their data files, modify those data files, update their version of a checksum, but an attacker couldn't modify them because that attacker doesn't have the information necessary to modify the version of the checksum. If you want to know how strong it is or whether it's strong, there's a journal article on that one.
They could modify it, or they could modify it without being detected?
Without being detected. This is an active detection mechanism. Detect only. No prevention, right? Where to prevent, we know what we have to do. We have to limit sharing or limit functionality. And there will be disagreements, I'm sure. Here's another interesting idea. It's the concept of end-version programming. This is like what the space shuttle uses and stuff like that. And the principle here is that we have, say, a bunch of programs. It runs program 1, takes the output, feeds it to program 2. We have 3 versions of program 1, presumably written by independent programmers to meet some very good specifications, and they all run simultaneously, and we have 3 times the software and 3 times the hardware. And we have a voter here, and if the virus causes some output of V1 of P1 to be incorrect, then that output gets voted out by the voter before being fed on through the systems. This is the hardware of TMR applied to software. The problems are, it's very expensive. Hard to do. The hard to do at present seems to indicate that you can almost never get 3 programmers to write even a trivial program so that they always give the same output, including all exceptions, including, you know, the round-off error being treated in different ways, the sequence in which things are performed, etc. If it is that close, it may be possible to infect all 3 at once, since we have a triplicated program doing the infecting. Finally, of course, it's not guaranteed against intentional attacks. These things are all designed to take care of the situation for random errors, and there has been almost no work on defenses against purposeful errors, that is, purposeful integrity corruption versus the non-deterministic assumptions.
Why do the programs really have to be different? Surely if you could count on, if it was essentially different independent copies of the same program, but you could count on the virus getting to one before the others,
Well,
you would have a
but
chance.
the question is, can you count on it getting to one before the others? And,
You can't limit
and you know,
that.
is everything going to run in lockstep? And if so, I'm going to have 3 versions of the virus infecting all 3 copies of those programs simultaneously.
Yeah.
It's the problem comes really in that there has to be some mechanism by which the computer performs those normal operations that people depend on. Whatever that mechanism is, a virus is no different than a normal user program. So it'll do whatever a normal user program would do to do those sorts of activities. Let's see. Here's an augmented version of self-defense. It's self-correcting. Essentially, we use the previous self-defense to detect an error, and we correct it using redundancy. An example is we used 2 versions of the program. Let's see, there's a program available for PCs and things like that called Mirror that keeps a mirror image. A mirror image is not very good from the standpoint of protection. If I know you're using it, it's very easy to infect both the original and the mirror. In fact, maybe I could infect the mirror only, and then you'll detect the difference and correct. But however you do this detection, presumably you want to use some of the redundancy to cure the problem. This might be valid for backups. Okay, you do backups, and if something gets modified, well, the real problem here is what's illicit and what's licit modification. The problems: V may modify the redundant part to accept or propagate the virus. By the time P1 gets to itself, it may already look clean. That is, I have written viruses that when you run the infected program, by the time the program actually runs, it's indifferentiable from before it was infected. So by the time it runs, it looks at itself and says, oh, I'm fine. And it works great. And it doesn't matter what self-defense detection mechanism you use in that particular case. Detection may fail. Of course, this can do an infection before it corrects itself, right? So the virus can still spread, but, you know, we're starting to really look hard now, you know. Here's a good one. This one will never work. Just ask it. Ask a normal person that uses your computer if this will work. User awareness. Every time a file is opened for write, you notify the user, or if you want to get hardcore about it, you ask the user for permission. Here, this guy is, oh my God. Well, if you have to ask the owner, you're in real serious problems, because then you wait until the owner comes home, you know. If it's illegitimate, and the user knows it, and the everything's okay isn't used by default, so often that it becomes automatic, then only authorized files may become infected. All right, well, I mean, there's some obvious problems. How do we educate our users? I mean, it's tough enough to get my users to type the return key at the end of making an entry, much less to know whether zz.batcom4 is appropriate to modify from spreadsheet 39. This, of course, doesn't prevent all viruses. It only prevents viruses that infect detected unauthorized files. And the overhead, of course, may be severe. In particular, imagine you have a large database, and everybody that uses that database has to say okay to every file that it ever writes. I mean, probably you don't want them to know all the files that are written. How about instruments? We'll use instrumentation. Viruses are normal user programs. That presents a problem. What it means is whatever statistic you choose, there's some virus that can be designed to sneak under that statistic. As you lower the detection threshold, legitimate software begins to get caught. As you lower it more and more and more, you find you have to verify all the software that's detected or abandon it. So what you end up doing is I don't trust it, I don't trust it. Finally, you detect all software as potentially a virus. You have to verify every piece of software in your system or abandon it all. In which case, of course, the attacker has really won big. Well, it's instrumentation is NC complete for limited verification. Verification covers. Here's the issue. We want to verify that a program does the right thing. Okay. It's NP complete right now to verify that a program does the right thing. That is to check that it meets its specifications. Of course, if its specifications are online, an intelligent virus can modify the specifications also. But that's another problem altogether. Verification covers sufficiency, not necessity. That is, the current theory of how you verify programs says this program does indeed eventually produce the results that you said that it should produce. It doesn't mean that it doesn't do anything else. And there's no theory for doesn't do anything else. In fact, if there was a theory that let us have both of them, that means that we would have a theory that would tell us automatically that not only does this program get the job done, but it's the most efficient program that ever gets the job done. Okay? Because otherwise there'd be something extra in it. Which means, boy, I got a good idea. I'll put in a specification, give it an empty program, tell it to fix itself. and our system will implement the optimal program for that specification. This is great. What a boon to programming. Well, so the problem is there's no theory. We don't have any good theory for integrity. Well, of course, the people don't necessarily have such great integrity either, so who do we depend on to get us our theory? All right, the theory is sort of fun to talk about and all this stuff. But really, without an experiment, you really have nothing. Because when we started this thing, I said, oh, this is a great idea. I wonder how many hours it's going to take to do an infection. How many years it's going to take to spread through a computer system. So we performed some experiments to demonstrate feasibility, determine infection times, and help predict attack times. Always got permission before we did anything. When you do this sort of stuff, often you'll come across a system implementation flaw that would let you take the system over or something without doing this stuff. And of course, you have to meticulously avoid those things to have a valid experiment with a virus, because a virus is just a regular, legitimate user program. So of course, what we did exploit was security policy flaws. That is, the flaws in policy that allow us to both share information and run programs. And of course, I can't tell you whether Unix, VMS, Top20, MVS, SCOMP, PSS, VM, DOS, or any other thing might have been experimented with. Before I show you the results of the experiments, I'm going to give you a scenario. This was designed for an executive summary, and I think it's sufficient to scare most executives if they believe that it's possible to have a virus. Basically, here's a timeline of what happens. You have initial infection when a user starts a virus. Infection, that's every time an infected program is run, more infection happens. Over that period of time, it's called the spread time. The virus spreads and maybe evolves as it spreads. This one will, of course. Eventually, it's taken over. What that means is that everything's infected. By the way, there's now a formal proof that as t goes to infinity, everything that can be infected does get infected. Based on, a variety of foolishness, assumptions. Relatively valid assumptions. Things like, eventually, every program will get run. See? That's not such a bad assumption. Delay time. Well, let's see. There's this period of time between everything's taken over and I do some damage. And if I make that a week or a month or a year or a couple of years, it may be that our backup tapes start to contain all sorts of copies of all these viruses, and of course we don't even know they're there yet. Finally, some event occurs, and the trigger is pulled, and then of course the damage is done. I'll quickly review the experimental results. Size of the virus is from 1/10 of a line to 200 lines of code in most of our experiments. Infection time is from 1/10 of a second to 20 seconds. 30 seconds to 48 hours to take over the whole computer. That's a real thriller. 48 hours, that's what happens on a Friday afternoon when everybody leaves, you plant a virus. It takes about 2 days before somebody comes in and starts using it. Maybe it's more than that, 7,200. Any delay time can be used, any event can be used to trigger, arbitrary damage can be done. And here we have this scary little virus, E, which some of you may or may not have actually seen versions of. Some employee A, perhaps disgruntled, writes a PC program containing E. Some employee B eventually uploads the infected program from a PC. E spreads and evolves through company computers, encrypts information on backup tapes as it goes, of course decrypting them when you bring them back from backups, using a key that's stored in a temporary file in the system. Oh, gee, employee A's access to the system is terminated. Maybe you changed his password. So the key maybe was his encrypted version of his password. All files are then deleted by E. Backups, of course, are useless because you bring them back, they're all encrypted. And in fact, nothing really works until employee enters his secret code, from the Bahamas to do it. You'll never know that that thing happened unless it prints out a message that says Merry Christmas. If it doesn't print out a Merry Christmas message, you're never going to know it's there. some people suggested, oh, I know what I'll do. I'll take the runtime of programs. I'll examine the runtime of programs, and if the runtime becomes excessively large, there must be some problem there. The problem is that the theoretical result here says that if I know how long a program's going to run, I can tell you what the result's going to be ahead of time. Because I can have a different branch for every possibility that takes more and more time, and therefore just predict the runtime, and I've already got the solution to the problem, so I never had to run the program. Next, we went to a Bell-LaPadula-based system. March 1984, negotiations began. By July, we actually performed experiments. This was some proprietary UNIVAC 1108-based system. In fact, if I told you the name of the operating system, nobody would have heard of it. It exists only in some room somewhere where nobody is allowed to go. The purpose is to demonstrate feasibility. Performance was not an issue. In particular, I had never programmed in 1108, nor used their operating system. Of course, nobody else has either. It took 18 hours. It took 20 seconds to do an infection. That was pretty sad. I'll tell you why it took that long. It's because it consisted of 200 lines of Fortran, 10 lines of assembler, and 50 lines of command files. Now, like the Fortran program wrote command files and then ran an assembly program to interpret the command files to generate another Fortran program. Not a very quick program. Capabilities, well, it demonstrated the ability to cross user boundaries and move up security levels, unclassified to classified to secret to top secret to whatever's above that. Oh, okay. So when I went to do this presentation, the person that wrote the system was there. The guy in charge of security was there. A whole set of people in the room, maybe 10 people who were really there. And I explained, here's what I'm going to do. I'm going to demonstrate a virus that an unclassified user can enter into your system, and it will spread up through security levels. And the guy said, it's not possible, you can't do it, absolutely impossible. This is great. Okay, if you've ever set up a demo in a room where the guy that created it is swearing up and down it's impossible, it's just what you want, you know. So I demonstrated it, and there it goes. And he is, so he said, how did you do it? And I explained it to him, and he got really ticked off. And he said, that's nothing. In a half of an hour, I could write one that takes 1/10 of a second, and it's completely undetectable. I said, that's the point. After presenting this at the NBS conference very soon after that, the Trusted System Evaluation criteria was accepted. This is the criterion that says that that's a sufficient security system for multi-level military use.
Military intelligence.
Well, that's right. Military intelligence is a contradictory term. All right, experiments are nifty. I mean, they really do things to people, but they probably some people's experiments have done things to the people in this room. Instrumentation was really what we wanted to do to find out how bad the problem was, because it was sort of unbelievable in my mind that 30 minutes was really the average time to take over a time-sharing system. I was like, you know, let's be reasonable. Maybe a day or two, you know, please, make it longer, please. August '84, we started instrumentation, whatever systems. The purpose was to confirm previous results, measure attack times, improve security, protection maybe. It took 8 hours to develop the instrumentation. I realize that's very exciting to you, to know how long it took me to write a program. Minimum, average, maximum time. Well, 30 seconds was the minimum time that we determined that somebody could have taken over the entire system. That's right, if somebody would have happened to plant a virus at just the right time in just the right place, 30 seconds later the world would be his. 48 hours, that's on weekend. 30 minutes, again, was the average. By the way, if you put a program on the bulletin board, say, here's a program, feel free to run it, who's the first person who's going to run it? Systems administrator, that's right. Which means you've taken over right away, unless you're reasonable about the way you do things. One of the interesting things that happens is that we identify a set of social users. You've heard of prostitutes, right? That's just what this is. They're social users, people that run a lot of other people's programs and people whose programs are depended on by a lot of other people. And what we tried to do was explain to these people that kept sharing needles about. So we made several suggestions. We tried a subsequent experiment to see how quickly a program would have propagated through the system if we announced it on the bulletin board. And it was an innocuous program, not a virus at all, just something that printed out good passwords. And what we found out was that somebody, after the first experiment, somebody that knew about the experiments came in and looked at it and said, "Hey, Fred Cohen wrote that. Don't anybody run it no matter what." Didn't even check to see what it did or anything for it. So he invalidated the experiment. And it took an hour and a half to take over. Well, one suggestion is, if you're the sysop, don't run other people's programs. And in particular, you can very trivially modify the operating system so that if you're the sysop and you try to run somebody else's program, you just can't do it unless there's something special that you do to say, "I'm going to do this stupid thing." Like it says, "Do you want to do that stupid thing?" And you say, "Yes," and they say, "Are you sure?" And if they say yes, then you don't do it. Because we like to promote people that aren't sure they want to do stupid things. Ask them questions that don't always have the same answer, so that they don't get used to just defaulting it. And of course, the social users were given extra accounts for running other people's programs. It said, when you're going to run people's programs, when you normally log in, do this. When you want to maintain the editor, don't do it in the same account where you run other people's programs. Quickly summarize some of the viral experiments to date. All these you've heard about. This is how long it takes to write. At this point in time, about 6 minutes is how long it takes to write a virus. And that's if you don't know a lot about writing viruses. I'm now at the point where, given about 1 minute on Unix, I have no problem generating 3 or 4. This is how long it takes to do an infection. A half second, that's the 20 seconds you've told about. Let's see, if you write one in the command language, I think we're going to show you one that's written in command language that runs at about 2 seconds. Lines of code, well, they can get quite small, 1/10 of a line of code. The smallest virus we know of is 11 characters in the command language of that operating system I have been telling you about that I can't tell you about. This is how many trials we've done. Sort of the interesting ones are the records. So I'll tell you the records. The record is, you write it in about 6 minutes. It takes 1/10 of a line of code. It takes about 1 second to do infection. Infection time, the record right now, this is all based on a standard IBM PC type performance. Not a fast processor, not a fast disk, anything like that. 0.2 seconds for an infection. Probably you could get it faster if you're on a Cray or something, but PC network is sort of interesting. Now I can talk about this one because somebody else published the result. Standard IBM PC net, 60 computers. Took about a week for some graduate students at UT El Paso to write a virus. Took less than a second to infect, about 100 lines of code, and they performed one trial, and then they had a very frenzied effort and never did it again because it took over the entire system in 30 seconds. As 60 PCs networked together in 30 seconds. Well, they were, so they got scared off quick. Any general purpose computer susceptible, development environments are especially vulnerable. Networks, of course, are vulnerable. We all know about that. Research environments are terribly vulnerable because we all share programs and it's all open and that's how we get things done and that's how we get hurt. Oh, here's a good one. Any system allows programming as a target. You'll see.
What about response to non-infected virus?
What about what?
Some company mini computers.
Well, if I have not done a particular experiment on one of those systems to determine that. However, it is my understanding that for many years now, many people have been doing very similar experiments, and I suspect that if you can get in there and modify the programs, you can infect the phone system. But I already know, I've been told by somebody that I have reason to believe truly knows, that 3 people from random pay telephones in the United States in 5 minutes can shut down the entire telephone system in the U.S. Not with a virus, just, by knowing what to do. So I'm not worried about a virus in the phone system.
There have also been documented cases of a person who was demonstrating some phone hackers on a bulletin board, and he had his phone bill come, and it was a real surprise. They just walked in, wrecked the database, and he came over with a phone bill 1,000 pages long.
Well, I mean, if you want to discuss general security threats, I mean, there's all sorts of stuff. There's the reporter who was reporting about hackers and who received tons and tons and tons of stuff on his front lawn that he had ordered through credit cards that he never knew existed. And he wrote subsequent articles saying how painful it was. But I don't think he ever said anything mean about hackers anyway. He scared them off.
Hackers is the IS manager in Colorado. It's the best way to keep hackers out of his system. If anyone run a hacker's bulletin board out of his system and actually stay a step ahead of them.
Like I said, another time I'll talk to you about other things. Researchers, just to give you an idea of the activity in the field. We're coming close to a close. So all those people that had the big questions, we're ready for you. I'm sorry if I ran over in time. It was because I had to answer too many questions that I was going to answer anyway, I hope. In '84, there was one person, that was me, wrote 2 papers. There was one news story. 1983, there was one person, but, nothing happened except some experiment. 85, 2 researchers at the university with 5 papers, 5 people I know of in the government with 3 papers in their private places, about 25 news stories, 3 of which were in the U.S. 86, there were 10 university researchers with 15 papers, 25 to 50 people in the government working on it with 20 papers at various classified conferences that I've heard of. Who knows about industry? Well over 100 stories, mostly in Europe, under 10 total in the United States. 1987, well, things began to grow. At least the newspapers, they were still under 187. I think 88, we can now say that the U.S. has caught up to Europe in terms of newspaper stories about computer viruses. Maybe we will surpass them very quickly. I know of some number of real-world attacks that have been reported by others, and this is just a little list. There's Lehigh. There was one variety that we know of, more than 250 were caught. I'm absolutely certain of that. U of Maryland, there was one variety, more than 250 were caught. This spread to some other universities. Hebrew University, one variety, well over 1,000 computers were caught there. It spread through various places in Israel, eventually got into several companies in the United States. That's right, transborder. There are 4 that I know of for the Amiga. They've been publicized on the Amiga bulletin boards, and over 1,000 Amiga users have been caught. IBM, if you consider the Christmas card a virus, which is a matter of definition, that is the empty program a program? That is, you understand that it didn't actually infect another program, but if the empty program is a program, it infected the nothing program. Well, you find when you get to mathematical definitions of this stuff, it's very difficult to talk about what a program is relative to a Turing machine. It's hard to define multi-programming environments, so it's hard to do mathematical proof. NASA, well, there's this thing that several hundred of them got infected. This is a 90% probable attack, and the reason I say that is the first week that this thing happened, they said it was viruses, and then they got talked to, and then they said it's not a virus, it's not a virus. Meanwhile, in about a month and a half, the Chaos Computer Club in Germany is going to come out and describe how the anonymous person that they heard of that launched this attack, and show how it works. The anonymous person that they know of, the Chaos Computer Group, that's rather well known for their ability to find anonymous people even though they never leave home. University of Pittsburgh, more than 10 were infected. That's about 50-50 chance. I've heard people say that it's true and people say that it's not true, so I say it's 50-50. I got a mysterious, well, the IRS. Well, the claim from several very legitimate sources is that there were approximately 3 viruses put into the IRS computers in Philadelphia. I got called from the IRS about it, and they subsequently decided that they couldn't talk to me after talking to the NSA, who also has this thing, they protect their thing. Well, I think only one computer was involved. I understand that there were some meetings in the White House about this, and from somebody that was at one of those meetings who said that it was discussed with the national security people and stuff like that. But it's still, this is not good enough for me to say it's 100% sure, because I haven't seen a copy and there's still people denying it. truck stops, well, one of the guys that writes programs for one of these national networks of truck stops took over the system from a previous person, and he described things that looked like a virus, that sounded like a virus, but I'm not absolutely certain because I haven't seen the code, and he's not a good enough computer expert to really know what the difference is. The Bank of North Carolina in Florida. That's all right. In Cincinnati, we have the First Third Bank. I frankly, I never could understand why anybody would put money into the First Third Bank. I'd be real upset, because
Be worse than the second, third bank.
right, that's what I was looking for. Like, why make the Second Third Bank? Maybe they've improved it. The Bank of North Carolina in Florida, just yesterday reported that they had a virus that was slowing down their system to the point where depositing a check took 3 minutes. That is, after all the paperwork, tell a computer deposit this amount into this account, 3 seconds. 3 seconds later, it would say okay. Now, if you understand the banking industry, which probably some of you do, a couple of seconds here and there gets very nasty. In particular, things are done on a basis where, interbank transfers, you can't do it 1 every 3 seconds. You cannot transfer very much money in a day.
Why didn't you do that earlier?
They had some real serious problems with that. There was a strike in Germany about 1.5 years, 2 years ago, where the programmers who were going on strike, before going on strike, left a nasty thing around. And what happened there was, after about a week, the computer slowed down to the point where it was unusable. They went to backups, 1-week-old backups, and in another week it was all slowed down again. They went to now 3-week-old, but originally 2-week-old, so it's now 3-week-old backups. And the computer slowed down again. And they went to 4 weeks old, it was a week later, so it's now 5-week-old backups, and the computer ran smoothly. Now, so that's 5 weeks of lost work on that computer system. That's pretty severe. In this particular case, of course, if the employees would have known a couple months ahead of time they were going on strike, they could have done much better. Hewlett-Packard has substantially agreed to the fact that more than 10 of their PCs were caught up by a virus, and after trying to track this thing down, I discovered that there's some employees of a company in Southern California who were playing with an evolutionary virus, and they thought they were all safe until one of their friends at Hewlett-Packard called them up on the phone and said, "Hey, remember that thing you were playing with the other day? How do we stop it?" On CompuServe, there was a virus put in that got to several Macintoshes, more than 50 of those got it. These are all the relatively certain ones. There are many, many other cases that we've heard reports of that we haven't gotten enough verification to get it up to this level of certainty yet. Finally, psychological effects. Gee, after you do an experiment, even though it's a safe experiment, people sure don't want you to do any more. And I don't go into all the business of this, but there's some real, I guess the feeling among systems administrators are that they would rather not know how bad the problem is than have to recognize that it exists. Programmers on a computer system feel as if their domain is like their body. And when they have their domain destroyed by something like this, they feel like they've been personally assaulted. And in the language of the rape crisis centers, we have to breed survivors, not victims. Finally, a quick overview of viruses. Tracing them back from their origin in November of '83. Evolution and replication. We've looked at computational aspects, defenses and attacks, simulations of attacks, attacks on untrusted and trusted computing bases, imperfect and perfect defenses. The imperfect we've gone into detection and cure, complexity and decidability issues, integrity via complexity, redundancy for cure, automated analysis for co-sets, provably secure networks, generalized information flow analysis, cryptographic checksums, public key checksums. Film applications have come out of this, ways of assuring that nobody sends you film to your film processing plant in the general sense of film, that you process even though it's not legitimately your film. Antiviral PC programming, classification schemes, the fact that it spreads to all reachable programs eventually. There's an integrity theory that's currently being developed, secure file servers, the digital diode, which is a piece of electronics for implementing provably secure POSET networks. There are 3 versions of PC-based networks, that is trusted file servers with limited functionality. And now we're into 88. So now, unanswered questions, please.
Just a sec. We ran about a half an hour over, so we probably ought to take a 15-second break, and everybody that desperately has to leave and is completely uninterested in all this stuff can split.
A sterile environment, which is visible to the user, and that there's defense mechanisms and processes the user does not have to know about, that he's just safe. Perfect prophylactic technique. However, in the real world, we all are concerned with health. We all sterilize, wash food, so we are used to taking extra precautions to prevent our bodies from being infected. Do you think it would be difficult for users to make that analogy to their body, which is their body of programs, to wash their programs, so to speak?
Yeah, in fact, there's a paper that I've written on this. The basic premise here is that it's like safe sex, essentially. All the things are the same. You don't boot your system with somebody else's disks. You don't run other people's programs without having the sources and examining them. The concept of integrity bureaus that look at source programs, verify that they don't have any inobvious or difficult to understand features or purposeful bugs, and then they give a certification. They compile it with their clean compiler, give a cryptographic checksum, which gets sent independently to the customer so that they can verify that the distribution is legitimate. A whole sets of these things. I mean, you understand, in an hour or an hour and a half, we got 5 years of research. But we're looking at it, and I happen to agree. I think that user awareness is a vital part of any protection system, as protection is an activity. It's not something you buy. On the other hand, I don't know how to tell my secretary how to understand what that computer does to the point where she can defend herself. So I'd like to do whatever I can to provide automated protection, or at least determine what automated protection can and cannot do, and what I have to teach that person and what I don't have to do. So, there was a question in here?
Can we ever stay ahead of it though? Because you look at the history of copy protection. For every new copy protection scheme that came out, there was at least a dozen schemes that were breaking. I get the impression that the best we can do is just try to stay ahead of it.
Survival of the fittest is the present situation. It may be the situation for a long time. In reality, these POSET networks, where you don't have this global communications, work for a great number of applications. I've designed several systems now based on the POSET, and there are other nice side effects, like you have to organize what you do in terms of information flows and how things work, to the extent where debugging is very simple, because you know the possible sources of errors, and there are no real deep subtleties about, the financial package changed this temporary file, which happened to be the same thing that was used by the data entry package, and that's what caused this subtle bug. You don't get that because we've controlled the way information flows. So I think that there is an opportunity to improve the way we do other things and also improve protection. But in general, survival of the fittest is how it is and how it's likely to be. And hopefully we can make things very fit.
I don't think it's going to be necessary, at least I hope it's not, that every secretary learn how to read every line of every computer language, just in the same way that a human being like in this room, I'd probably be surprised if more than 5 people that understand how the major histocompatibility complex identifies the surface of each cell in the body so it can be recognized as self or non-self, and how it varies between an individual based on the action of the thymus gland during the fetus and the birth. We protect ourselves by an essential self and non-self mechanism.
But there's a fundamental distinction here that you're missing.
Programs are formless in some sense.
Well, I don't know about that, but there's a fundamental thing that you're missing here, and that is that these bodily defenses are not typically intentional attacks. We're defending against random occurrences, presumably, whereas if you look at biological warfare, there's no hope that anybody's body is going to develop a way to defend off against intentional biological attacks. So that's a fundamental distinction, is that these attacks tend to be intentional, designed to violate these protections that we put up. And there's a very interesting set of issues about what has to be kept secret and what doesn't have to be kept secret in order to have viable protection systems. I don't want anything to be kept secret if it doesn't have to be, but in the password, for example, has to be kept secret or people get into your account. So it's just not quite straightforwardly biological because of the attacker's intent.
I see parallels though.
The DNA sequence and the
human
sequence
immune
instruction.
system is incredibly local and robust, and yet still fails on occasion, and the human body eventually dies.
And so eventually computers aren't used anymore. Also,
I think it's one of the government agencies perhaps necessarily classified as operating systems as to be whether they're a secure kernel or not. Supposedly there's a secure Unix, and supposedly MPS is not secure.
when they say secure, they're talking about provably secure, which means they've done enough mathematical proof of what's going on to have a fairly substantial belief that the system properly implements the policy. The problem here is that the policy is not one of no programming, no sharing. It's a policy of protect secrecy, or protect secrecy and integrity, or a POSET. So, subject to the fact that the policy indeed is appropriate to limiting the spread of viruses, these systems do indeed limit the spread of viruses. But they do that by eliminating sharing and or the ability to write programs in a general purpose sort of way. So, yes, if you're willing to give one of those two up, you can be very, very safe. These systems are certainly applicable in certain circumstances, not in all.
We discussed techniques for perfect effect protection.
Yeah.
But what you really want to guard against is fatal types of infections that are really going to completely destroy your system.
No. In fact, that's not what I'd want to defend against at all, because that's very easy to undo, because I know it happened. The things I'm concerned about are an infection that gets into my steel manufacturing plant and occasionally and subtly causes my steel to be lower grade than it normally should be. And I blame it on temperature deviations or on a bad sensor. And it happens reoccurring randomly and costs me money time after time after time in my business, while my competitor who launched that attack is sitting there with a magnificent steel manufacturing facility, and where that person's making progress, I'm fighting just to stay even. So the very showy, flash things on the screen, destroy everything in sight sort of virus is not, to me, the most devastating. It's the one that sits there and I never ever know it's there, and it just constantly eats away at my ability to exist. That's what really is disturbing about viruses to me.
You mentioned that the viruses will spread eventually all over the network, so whoever put this virus into the system will get infected after all.
Well, but no. In fact, you can design viruses to be specifically targeted. The proof was that in general, if we have an infection mechanism and a set of users randomly running programs with some type of statistics, as t goes to infinity, all programs infectable by that virus will be infected by that virus. Not a surprising proof. I mean, probably something that somebody should bother to do sometime.
That implies that the person who invented that particular virus can detect this virus.
No. What it means is there's no.
What you just said.
It means there's intent. Suppose I design a virus that looks for particular places to go. It doesn't just choose any random path to get anywhere it can get to. It'll only infect things that have 1 as the first number in their user ID. It just won't infect you if you don't have that. And my user ID starts with a 2. It'll never come to me. So there are all sorts of ways of limiting it. Of course, every time you limit what it does, target it more specifically, it becomes more complicated. It probably has longer run times. It's probably more difficult to write, et cetera, et cetera. But there's no restriction on a virus that says it has to infect everything that can ever become infected by any virus. It can be targeted.
And along the same lines,
Okay.
just being infected isn't necessarily bad. You have a virus that infects everything and then destroys everyone's files except yours. So the fact that the author gets infected himself doesn't have to mean that any damage is done.
Well, actually, the space that's taken up
Yeah, but I
define
mean,
the safety.
but
That's certainly right. You can trigger the infection. You can carry any code you want. I mean, really, if you just think of it as a general purpose mechanism of taking my program and putting it into every program everywhere, then that's what it is. So
You know when T is 0 at that point, so you have backups which are safe for your own personal program.
well, in fact, the systems that I run were all written and compiled, unless I have sources, were written and compiled pre-1983, which is, I know, when it all started.
you know when yours all started.
Well, yeah, I know that there's no substantial evidence that anybody was doing anything serious with them before that. But, you know, so who knows what's safe.
What about Shockwave Writer?
That's a science fiction book, which I, by the way, have never read, but I heard about. But that's not necessarily sufficient for me to believe that everything was infected before then.
And I heard a report in 1982 about viruses on the West Coast. Personally, I was told that A, viruses exist, and that antivenom was another term that was given to me at the same time. This is 1982 now.
Well, I believe what you're saying. I have to go based on evidence, okay? That is, when I talk about evidence, were there any articles published? Were there enough people that saw the code? Even if it existed, my important work was not the splash of light that comes up that says there's an idea for a virus. It's the 5 years of defenses, the proofs of the undecidability, the proofs of how far things can spread, the post-set networks, the complexity-based protections. I mean, it's the defenses that are tough. I mean, I'm willing to stipulate that anybody could think of a virus, and that's, in fact, why I was willing to publish about viruses, because I knew that if anybody can think these things up and they're that simple to write, then we better get a lot of people stirred up and working on defense. So, I mean, you can't abandon your hopes of defense, but that's how it is.
You have referred several times to publications you have created. Are they available? What are they?
Computers and Security is an IFIPS journal, and it comes out, I guess, every other month now, and I have one every month last year, and the April issue, April 88, is going to have, I think, 4 papers on viral defenses, and Steve White has copies of 10 or 15 papers of mine on this, and my PhD thesis, and various other stuff. So certainly that's a good starting point if you want to read for a couple of weeks.
Do you have any estimates of the cost of the defense against viruses now and in the future?
I know that things like what they did at Lehigh are not likely to be the solution to the problem. See, what they did to defend there was they wrote something that detected whether command.com was modified, and if so, replaced it. Actually, 2 programs. Well, that's great, but everybody runs that program once. They all think they're safe, and 6 months later, somebody comes back with their floppy disk that they left home over the winter when they went on vacation. And now it's all back again. That is, those defenses that they're leaving there aren't leaving any continuous or lasting protection. I think that these complexity-based defenses are very strong. The self-defense through complexity is the sort of thing that I think will work very well against executable files. The problem here is that you can infect source programs. You can infect intermediate files. You can infect anything that can be interpreted. So I don't think defenses against that stuff is ever going to really be very strong. But I truly believe in defenses against executable self-defense as being very viable, and we could use it right now and substantially reduce the threat. So,
quick identification. In 1976 at RPI, we wrote a program called Wabbits, which basically resubmitted itself twice, and so it would tie up the operating system. How would that be classified?
Well, I would call that a self-replicating program, but it doesn't infect. The infection, this is why they...
program?
That's the question, okay? It's a matter of definition. The thing that's nasty, nasty, nasty about viruses that I talk about, if you want viruses that don't infect the null program, is that they persist and they spread from program to program. So they reach the transitive closure of information flow, and they can remain forever, okay? And that's the real hazard. That's what makes them severe relative to simple programs that self-replicate. Now, the Christmas card, of course, is an example of a program that self-replicates that was fairly severe. It could have been much more severe if it had infected other programs because you could not have cured it just by eliminating the Christmas card.
Just change its name, probably, disaster.
Maybe not
Well,
after that.
actually not, because a person had to be induced to run it. And if the name had changed arbitrarily, they'd be unlikely to do that.
Yeah, well, but certainly if it had infected random other programs. Let me give you something scary. Let us imagine that that Christmas card, for the first 15 replications, infected other programs with some completely different virus. Now, you might imagine that you thought you traced down the Christmas virus. But what you traced was what they wanted you to know had existed. And when you wiped that out, all you did was delay for 6 or 9 or 12 months the ultimate damage, which is going to be severe. Now, I'm not saying they did it, but anybody here that knows how to program could probably write a program to do that variation on that Christmas card.
Oh, sure, yeah.
And that's the difference between infection and replication.
You evidently have done a lot of SWAT teamwork or target teamwork doing this. What's your technique so that you know everything's been affected? Every PC or every computer comes out and says, "Hi, I've been infected."
I've done very few experiments on live systems. The experiments that I've done on live systems, I do a combination of things. One thing is, I keep all the code encrypted. What it does is decrypts itself, performs an infection only against a list of things that I say it's okay to infect. It does it as I observe and asks me at my terminal, can I do this infection? Upon doing that infection, it puts traces into the operating system. Because the normal tracing in the operating system keeps track of certain things. So I make identifiable traces to the operating system so I know that this thing got there. And then what it infects with is a re-encrypted version of itself. So that, by the way, it's fairly nasty to determine that if you use a different key for every encryption and decryption. It's real tough to trace it down. But that's another factor altogether. So that's what I do, and then I keep copies of the original programs pre-infection, so that after I've done the infection and shown the experimental results, I replace all the infected programs with the previous files that were uninfected, checking against all these traces, and I don't do it when backups are allowed. You know, you lock the key to the room where the backup tapes are there, and stuff like that. And then we keep other traces of activities on the system, so we can detect if anybody copied one of these programs or something like that. So that's the sort of, incredible amount of feats that I go through to try to protect these
So
things.
you really have not gone after major production sites where you can do, in other words, you didn't go after a big IBM location or a big bank.
Oh, I don't want to get thrown in jail.
No, with their permission. With their permission, you come in.
No, I wouldn't do that even with their permission because it's so hazardous.
Yeah.
Somebody keeps a copy somewhere it doesn't, you don't know what's going to happen. So it's not sane to perform these experiments in a live environment where people are depending on it.
Besides, suppose you ran in a live environment where there was already another virus hanging around.
Then you would be blamed for that.
Yeah, this is why I asked the question.
We're running pretty long. Let's take one more question and then stop the formal part of it.
What about hardware changes? For example, one thing that came to mind when you talked was worm drives. Would having a write one storage system as opposed to a rewrite storage system alter the infectability?
Well, in general, you can't infect something if you can't modify it. That is, if you can make it, read only. But of course, then you can't modify it. So that's a normal function of computers. Worm drives are not particularly safe because the way a worm has to be designed for it to work right, you have to be able to replace a file, or else you can never replace anything. So the way you replace it is by modifying the bits to say this one's all used up and here's another copy over here. You might be able to go to the backup for backups, but of course on a worm drive I can overwrite any bit. I can make anything a 1, I just can't make it back into 0. Of course now I can make them back into zeros, so even that doesn't count. But there's all sorts of them. If you keep every keystroke ever typed, you just back up through all those keystrokes until you find the originator of this virus, and then you know who it is, and you can trace everywhere it got to. Chances are it got to everywhere. But okay, I'll replicate all the keystrokes from everybody else independent of all that stuff, but that's a little bit of a price to pay.
You could write a hardware storage device which is totally hardware, not modifiable. So,
Well, I've suggested to people that if they don't want to be able to write onto a disk, that they cut the wire that goes to the write head. It works great. You can't write that disk, but that's what you have. You have a big read-only memory, and you can't write programs. So that was one of the conditions. If you can't write programs, you can't write viruses. Viruses are programs.
I've got to give Fred a big hand for this.